How much energy is being transferred to the Earth? How much energy is transferred to the moon by the gravitational force from the Earth? It's got to be none. I think most of you guys got that right. Okay, now the explanation was slightly off, or I was being a little bit too picky. Because the force is perpendicular to motion. Okay, that's what most of you guys said. That's good enough. Normally, I was hoping for a little bit more. This force doesn't have a component along the direction of motion because it's 90 degrees to it. Okay, so most of you guys said it's perpendicular, but you need to provide an explanation. Okay, you need to write it out as if the person who's reading it does not know what you're saying. If you said to someone, "Hey, dude, this is perpendicular to that," that's the reason why it doesn't transfer any energy. It's not going to make sense to anyone. Okay, so you have to provide a complete explanation. This force does not have a component along the direction of motion, which means that this force does not contribute to this motion. All right, so you have to be a little bit more precise in your explanations. Okay, another one is, a lot of you guys got this one right, except the explanations are a little bit weak. So you throw a ball in the downward direction, a second ball in the forward direction, right? So which ball is going to strike the ground while moving faster? Which one is going to have a larger final speed? All right, short answer is both of them will have the same speed. All right, and then the explanations got kind of murky for you guys. Because gravity is the only force acting. If gravity is the only force acting, the initial and the final mechanical energies will be the same, so mechanical energy remains constant. And in the initial case, most of you guys they're at the same height, so they will have the same potential, and this is the initial case, and they will also have the same kinetic energy. In the final case, just before impact, everything is going to be kinetic. So this means that in both cases, they're going to be moving at the same speed. All right, so your explanations were more like repetition or recitation of a definition. I was looking for more than that. I was looking for a concise explanation, because this is here, not only do they have the same potential energy, they also have the same kinetic energy. That's the reason why they have the same initial mechanical energy. On impact, they don't have any potential energy. Everything is kinetic, so that means that they're going to be moving at the same speed. All right, so question number 3, which one requires more work, stretching a strong spring or a weak spring the same distance? I think most of you guys got this right. All right, so you have to kind of go back to the definition of it. Okay, so the distance stretch is going to be the same. A strong spring is going to require more force, obviously. So the bigger the force is, the more work is going to be required. All right, so I think the explanations for that one was fairly good. All right, so boom, boom, boom. Okay, so pendulum move. And so what do we have? The pendulum snaps somehow, splash down. They will hit the water at 91 miles per hour. And if they were to jump, what's the question? If they were to jump straight down, do you think the outcome would have been the same? I got news for you guys. It's the same. Outcome is going to be the same, because ignoring friction, only force acting is gravity. They have the same initial mechanical energy because they're jumping from the same height. It's all potential. They will have the same final mechanical energy. In this case, it's going to be kinetic, so they will hit the ground at the same speed, or they will hit the water at the same speed. Here, they suffer the worst case scenario. They end up landing on the side. Okay, so if the worst case scenario is survivable here, it's going to be survivable there. Okay. And obviously, if you can survive the worst case scenario, you will survive the best case scenario. So it would have been the same. Okay. Lastly, we got the Canadian strongman. He's carrying a rock at a constant speed. He wasn't doing any work on the rock, obviously, because the motion and the force were 90 degrees to each other. Okay, so we got that. So the question is, why was he getting tired? The reason why he was getting tired is because while the motion is in the forward direction for his mass, all right, so he was getting displaced in this direction. The force of friction that he was generating, he was pushing up against the ground in the opposite direction. So the frictional force was in the opposite direction of the motion. Okay, so the negative work was being done on it. And as you well know, that frictional force depends on his apparent weight. This guy appears to weigh 410 pounds plus his own weight. So if this goes up, the frictional force is going to go up. The larger the frictional force is, the larger the amount of work that he was doing. So as a result, he was losing a lot of energy. So that's what's happening. Okay, guys, take care of the test.